Okay, let's see if this works. I haven't used this for a while. What we're going to be looking at is section 5.3. Now there's a fair amount in section 5.3, but I'm not going to be going into some of the Runge-Kutta aspects of it. But we're looking at how we can solve the higher order differential equation using the Euler method. Now the Euler method is a first order DE process, but we're going to adapt it by changing our higher order differential equation into a system of first order DEs and do Euler on all of those in the system simultaneously. But first, let's just remember what the Euler method was. Make sure everything's working right here. Yes, it is. Okay, so given a first order differential equation, y is some equal to some arrangement of t's and y's. Now, of course, we're assuming y is a function of t here, and we're given an initial value at time 0, y is equal to y0. What we want to do is to approximate the value of y at a spot that's pretty close to where we started. And Euler's approximation here is basically based on the differential in calculus 1. The value of y at t1 is approximately the known value plus, well, you go out the derivative, the tangent line, this distance. If you take your known value plus this bit, you get something that's approximately equal to y1. Now, if you wanted to go a little further, you can evaluate the derivative at, you can do one more step here, or more steps. The value of y at t2 is approximately, well, it's approximately the value we got just in the first step, plus we'll go out the derivative at t1, this distance. In this case, we're looking at t2 is t1 plus h. And we can keep this process up. Okay, the value at t3 is approximately the value we got for t2 plus h, the step size, times the derivative at t2. And these values over here, the derivative at t2, we can get that by plugging into this equation. Okay, so we want to do the Euler technique on a higher order DE, so we need to play around with the higher order DE and get it into a first order situation. Okay, so what I have here on the left is an equation that stands for a single differential equation of order m. So this is the mth derivative of y is some function of the independent variable t, y, and all the lower derivatives. Okay. Now, based on the order, the DE here, this is an order m. You're going to have m number of new variables. And we start with this way. X1 is going to stand for our function y. X2 will stand for the derivative of y, but notice that that's the derivative of x1. X3 will be the second derivative of y, but that's just the derivative, the first derivative of x2. X4 is the third derivative of y, which is just the first derivative of x3. That's supposed to be a 3 there. So you keep this up. Xm is the m minus first. That's supposed to be an m there, derivative of y, which would just be the derivative of the xm minus 1. Okay, now putting this together with, so anyway, what we do when we rewrite this and substitute, take this equation here, we have that the, okay, we want the mth derivative of y. So that would be xm prime is the mth derivative of y. So xm prime is going to be a function of the independent variable t, and y is x1, y prime is x2, y double prime is x3, and ym minus 1 is xm. Okay, and you don't have any derivatives over there. Now, when you put this thing in normal form, you list a system of first order differential equations. Okay. So here's one of them. Okay. That's a first order DE. The next one would be xm minus 1 prime, and that's just xm. Xm minus 2 prime will be xm minus 1, and so on down here to x3 prime. The derivative of x3 is x4. x2 prime is x3, and x1 prime is x2. So this is what we call normal form. Now there would be some initial values along with this. Let's do an example here. And this is problem number 4, page 259. We want to convert this fourth order differential equation into a system of first order DEs in normal form. So m equals 4 here, so we will have 4 variables. We'll have x1, x2, x3, and x4. Okay. x1 is y. x2 is y prime, which is same thing as x1 prime. x3 is y double prime, which is the same thing as x2 prime. And x4 is y triple prime, which is the same thing as x3 prime. Okay, so this is our differential equation. Let's write it in terms of these new variables. The fourth derivative of y is going to be the first derivative of x to the fourth. Okay. See, x4 prime is the fourth derivative of y. We don't give it a new name. We don't need another variable here for x5. Okay. This is x4 prime. The third derivative of y is x4. Then we have plus 7 times y. Well, y is just x1, is the cosine of t. So let's go through here. If we're going to put it in normal form, I need to have my primes on one side. So x4 prime is, get everything else on the other side. Let's add x4, subtract 7x1, and the cosine was already there. All right, now x3 prime is x4, is this guy. x2 prime is x3, and x1 prime is x2. Okay. So these 4 differential equations are the normal form. I need to also put in the initial values here. Y is 0, that means x1 evaluated at 0 is 1. x2 evaluated at 0, well, x2 is the first derivative. That's y prime, so x2 is 1. x3 is the second derivative. So x3 evaluated at 0 is 0, and x4 is the third derivative, and x4 evaluated at 0 is 2. So here is my answer. There. Okay, so that's how you change a higher order DE into a system of first order DEs. We're going to look at a way to find this, to solve this, at least numerically. There's a lot of stuff you can do with differential equations and linear algebra at the same time. As a matter of fact, many DE books are combination differential equations and linear algebra books. Okay, and it'd be nice to go into, I like working with systems of differential equations, and we'll do a little bit with them in this chapter. But all we want to do in this section is make a normal form out of it, and then to find a numerical solution for a higher order DE using a version of the Euler method. Okay, so this is number 11. I chose number 11 in the book because the odd answers are in the back of the book, and these problems are really, really long and messy. So I wanted to make sure I was getting it right. It took me about 4 times to get it right, not because it's hard, it's just that you have to be very careful and you have to be very organized. And so you need to plan how to work one of these problems. Okay, but the first thing is we're going to make this like problem 4 over here. We're going to make this a system of DEs in normal form. Yeah, we have a second order DE, so we're only going to need 2 variables here. We're going to need x1. Whoops. We're going to need an x1, and we're going to need an x2. x1 is always y1. x2 is the, excuse me, x1 is always y, excuse me. x2 is y prime, which is the same thing as x1 prime. Okay, now this DE is 1 plus t squared. Now, pardon me, I was having a sneezing fit there. So it's 1 plus t squared times y double prime. Well, y double prime is the first derivative of x2. Y prime is the same thing as x2. And y is the same thing as x1. Now, to put this in normal form, I need to solve for x2. So that would mean I add x1 to both sides, I subtract x2, and I divide by 1 over t squared. 1 over 1 plus t squared. So this is x2 prime, and x1 prime is x2. So this is my normal form. Let's put in some initial conditions here. Okay, let's see, x1 of 0 is 1, and x2 of 0 is negative 1. Okay, now what we're going to do is we're going to use, we want to figure out, can't read this. What we're trying to do is we're trying to approximate y at 1. Okay, we're going to be using, so this is the same thing as finding the approximate value of x1 at 1. We're going to be using Euler method with a step size of 0.025. Okay, and Euler says that x1 of some t1 value is approximately x1 at the previous value plus your step size times x1 prime at a previous value. But x1 prime is just the same thing as x2. Anyway, I've got it down here on the next page. Okay, so our steps are, well, T0 is 0. T1, you go by 0.25. T2, you go up another 0.25. T3, you go up another 0.25. And finally, for T4, we should be at 1. Okay, so let me write down what that means here in terms of the Euler formula here. Let's back up. We do know that x1 of 0 is 1. Now, x1 of 0.25 is approximately, well, it's the value that we know already, x1 of 0. Clean that up a little bit. Plus, okay, our step size times x1 prime of 0. But x1 prime is just parentheses in the wrong place. It's just x2 of 0. Okay. I'm going to fill in some numbers here in a minute. All right, now the next estimate will be at 0.5. And that's approximately the estimate we had at 0.25 plus the step size. Okay, right. I'm writing on a slate here. I can't see what I'm writing. It's really pretty difficult. So it's 0.25 times the derivative at 0.25. The derivative is the same thing as x2. Okay. Our next estimate will be at 0.75. And that will approximately be the estimate we have at 0.5 plus our step size times the derivative at 0.5, but the derivative is the same thing as x2. Okay. And finally, the estimate we have for 1 will be based on the estimate we had at 0.75 plus the step size times our estimated derivative, 0.75. Okay. Now, so that's the equations we're going to have to fill in here. Now, the thing about this is that we need to know something about x2. And we're going to be using the Euler formula on x2 simultaneously. And it works this way. x2 is some value, is approximately x2 of the previous value times the step size plus the step size times the derivative at the previous value. And here's my formula for the derivative. Okay. Because this is when we solved our derivative, where was it? Yeah, x2 prime was this thing. So what we have to do is we have to solve everything simultaneously. Let me go ahead and write down what we're going to be doing here. We know that x2 of 0 is -1. x2 of 0.25 is approximately x2 of 0 plus 0.25 times x2 prime of 0. Okay, and I'll have to figure that out too. x2, excuse me, x2 of 0.5 is going to be approximately x2 of 0.25 plus our step size times x2 prime of 0.25. And then x2 of 0.75 will approximately be what we had at 0.5 plus our step size times x2 prime of 0.75. And that's as far as we need to go, because our x1 only needed x2 at 0.75. Now, in order to fill out all of these, I need to know what x2 prime is at each of these things. So let me go ahead and put the formula in over here. I said the computations aren't hard. It's just you have to stay really, really organized. x2 prime of 0 is 1 over 1 plus 0 squared. x1 of 0 minus x2 of 0. Okay. For this one, we'll need x2 prime of 0.25. I got a mistake down here. Excuse me. Let me erase something. Okay. To do x2 prime of 0.25, I'll need to have 1 over 1 plus 0.25 squared times x1 of 2.25 minus x2 of 0.25. And to get x2 prime of 0.5, I'll need to have 1 plus 0.5 squared over x1 of 0.5 minus x2 of 0.5. Okay, now we're ready to start cooking here. Let me change my colors. Let's see. Oh, I need to change color. Good. Okay. Well, let's fit in what we have here. x1 of 0, I've got that. That's 1. 0.25. x2 of 0 is what? Negative 1. So x1 of 0.25 is 1, or at least approximately 1 minus 0.25 is 0.75. Okay, now I can go ahead and put that in here, but I have to have x2. So let's go over here. x2 of 0.25. Well, let's go ahead and fill this thing out here. I need to have x2 prime of 0. So that's 1. x1 of 0 is 1. x2 of 0 is negative 1. This is 1 times 2 is 2. So x2 of 0.25 is approximately equal to x2 of 0, which is negative 1, plus 0.25 times 2. And this is negative 1 and a plus 5 minus 0.5. Okay. Oops. All right. So now we're ready to go to this one here. x1 of 0.25, 0.75 plus 0.25 times x2 of 0.25, and we had that to be negative 0.5. So I've pushed the estimate out halfway, and I've got a 0.625. And here's where things get really messy, and I'll have to get the calculator and make sure I record all of these values accurately. Now the next one we need to know what, it's this. .625 plus 0.25 times whatever this thing is, x2 of 0.5. Okay. So x2 of 0.5, I need to know what x2 of 0.25 is, x2 prime of 0.25 is. Okay, so this is 1 over 1 plus 0.25 squared. x1 of 0.25, back up here, x1 of 0.25 is 0.75. Oops. Oh, man, this is really hard to write on this thing. At x2 of 0.25, we found that that's a negative 0.5. Okay, so when you get this, we have sorry I had to pause there. I wanted to make sure I was getting the right answer. It didn't sound right, so I checked it by some other computations that I had, and it was right. This is 1.176470588 and so on. Okay. So this thing is x2 of 0.25, which is minus 0.5 plus 0.25 times all of that. Okay. So this is negative 0.20588 Okay, that's x2 of 0.5. So let's go over here and plug that in here. That goes right here. Negative 0.20588 239 dot dot dot. And that gives us 0.57352 94118. Okay, I only have one more step to go, but they get increasingly messy. Okay. So this is going to be 0.573529418 plus 0.25 times whatever we got here, x2 of 0.75. Okay. And what we're going to have to do to figure that out is this. x1 of 0.5 is 0.625. x2 of 0.5 is this thing. 70588 23529. Okay, so keep hitting wrong buttons on my calculator, so I have to pause a minute. Okay. This is 0.66470588823. Okay. So when we go over here, x2 of 0.75 is approximately x2 of 0.5, which is negative 0.205823.529 plus 0.25 times this thing. Two, three, two, which is negative 0.039705. So 7 there. 8823. Okay. Okay, now when we go back, we're about done here. And plug that in here. We get 0.5636029412. Okay. So this is approximately the value at 1. Okay, so you can see it isn't really that hard. And if someone was a little more careful than me, and you can see it would be possible to make some sort of little program that plugged everything in where it was supposed to be, and you can maybe even build it in Excel, just have some macros or something, I don't know. But that's the process you go through here. Takes a while to work a problem. I think the one, so if there is one I've assigned on this section. These are really easy. Changing to a system in normal form is pretty straightforward. Using Euler to solve it is a little bit longer, and I suggest you try to follow the technique I've done. Is go ahead and write out your equations that you're going to fill in before you start putting numbers in. Okay, good luck.